invitation. It's my pleasure to review the experimental search for the chiral magnetic effect. So the previous speakers already give some introduction to heavy ion collisions to the CME, so that makes my life easier. But I will just give some brief introduction anyway. For chiral magnetic effect, the first thing is spin alignment in the magnetic field. If you have a very strong magnetic field, so particles will have their spin either aligned or anti-aligned with the magnetic field, depending on the electric charge. Then for the chirality or headedness, it means momentum will follow the same direction of spin or the opposite direction. We call it aligned or anti-aligned or right-handed, left-handed. So if, say, we have right-handed particles, then momentum and spin will follow the same direction. And in this case, we will have positive charge going up, negative charge going down. So this is a charge separation, or it's an electric current induced by the magnetic field. And notice, this is not the conventional Faraday induction, those kind of physics, because the magnetic field and the electric field, they have the same direction in the CME. So this is new physics. The CME physics has been shown to be correct in the condensed matter experiment. So this is just one of the early papers published in Nature. When they have the man-made material, they can put the chirality by hand into those material. Then when they look at the resistance as a function of magnetic field, when you increase the magnetic field, it's something like superconductivity. The resistance will drop quickly. And the data point can be described very well by the prediction with the CME. So this is very good evidence that the CME, the physics, the formulas, they work. And later, there's a whole industry of the CME search for semi-metal. And they got published in Nature in Science. So, but those are not my focus. My focus is the heavy ion collision. So in heavy ion collisions, we have different ways to generate chirality imbalance and to generate the magnetic field. So we have a few conditions. So first, if we have the deconfined system and quark-gluon plasma, we could have chiral symmetry restoration. In this case, quarks become almost massless. And when you have massless quark, you can talk about chirality and helicity. Then, if the whole system goes through some vacuum transition, then you can have a finite chirality chemical potential. So this is local parity variation. You will have a finite mu5. Then another condition is, in the initial stage of the collision, you have very energetic spectator proton. They pass through each other, generating very strong magnetic field on the order of 10 to the 18th Gauss. So once we have all these conditions, we have magnetic field, we have chirality imbalance, then magnetic field will polarize the spin of the quarks according to the electric charge. And say we have more right-handed quarks, then we will induce an electric current. And this is the same direction as the magnetic field. So if in heavy ion collisions we do observe CME, we will advance our knowledge in all these directions. So that has very different significance than the semi-metal experiment. Then in the experiment, what we are looking for is the charge separation across the reaction plane. The reaction plane on average, is perpendicular to the magnetic field. So that's observable. So if we do a Fourier expansion of the particle azimuthal angle, besides the conventional V1, V2, V3 terms, we can have an extra A1 term if we have the charge separation. And this A1 term will have opposite sign for positive and negative particles. So on average, if you average over all events for this quantity, you will see something like exactly 0. And it's expected because the mu5 flip sign from event to event. So if you average it, you get 0. We have global parity conservation. So instead, we have to look at the fluctuation of this thing. And for example, this lower right figure shows you the fluctuation of the net charge across the plane. Then in plane and out of plane, they look slightly different. They have different widths, and the difference is on the level of a few percent. So actually, this is a direct or more intuitive way to see that in plane and out of plane do look different. However, we want some better observable to better quantify this effect. So on the market, there are several CME hunting observables, like the gamma correlator, R correlator, signed balance function. So recently, we published a method paper to discuss this with a model called AVFD. So with this model, we figure out that all the three methods, if you put them on the same footing, they are sensitive to the signal in the same way. So the x-axis on the right figure is the true signal. That's the input for the model. Then you see the observable increase linearly with the signal, and they overlap with each other. So the three observables, they have the same sensitivity to the signal. And also, they have the same sensitivity to the background. So when this N5 over S is 0, it means pure background. So actually, all the observables are sensitive also to some finite background. But the, yes?
So how do you build your background for this
How do I what?
How do you build your background for this
Oh, so for this model, it can implement local charge conservation. Then local charge conservation coupled with two-particle correlation, you can have a finite background. And this is a pretty realistic way to do it. So with this knowledge, all those three methods are equivalent to each other. So in later slides, I will just focus on the most popular one, the gamma 112, that correlate two particles, alpha and beta, with a second-order event plane. And alpha and beta, they represent different charge sign. So if you do a simple expansion, you find it contains a V1 term, it contains A1 fluctuation term. And this is what we are looking for. But V1 should be charge independent, and it just got canceled. And there are some other background terms that are also largely canceled. But keep in mind, they do not completely cancel. So that's the pain of this analysis. I will also emphasize later. So if we do have a CME signal, it will cause delta gamma, which is opposite sign minus same sign, to be positive. So that's the signal we are looking for. So now I will show you some example of our past measurements of this gamma. So the upper left panel, we have this measurement of gamma as a function of centrality. And for centrality, 0 means very central collision. 70% or 80% means very peripheral collision. So blue are opposite sign, and red are same sign. We do see this charge separation for both gold-gold collisions and the copper-copper collisions. And later, we also see this charge separation effect in uranium-uranium. And we have the beam energy scan program, including the LHC energy, 2.7 TeV lead, and down to 200 GeV, 62, 39, 27, and so on, until 7 GeV. For most cases, you still see the effect. The blue is above the red. Maybe until 7 GeV, it's not so obvious, but we still have some small but finite signal. So looking at this, we should not be too optimistic. We have to keep in mind that we still have some background contamination from that in-plane, out-plane constellation, which is not complete. The background comes from flow-related, basically V2 or elliptic flow-related background, and some non-flow-related background, for example, digests. So for all those past 2 decades, we have been fighting against such background, how to get rid of them or control them. So one way to mitigate the background is to scale the delta gamma with V2 and the delta delta. So this is to mitigate the flow-related background. And delta delta is just the 2-particle correlation. So it's a simple coupling between flow and the 2-particle correlation. And by doing this, a good thing is we can compare the data with some model. And this figure shows you 8 panels of the comparison of the measurement in comparison with the AMPT model. So AMPT is a pure background model. So you can consider it's a background estimation for this kappa. So what we observe is at highest energy, like 2.7 TeV, the observable and the background are consistent with each other, meaning we are not supposed to see an effect there. And similarly, at the lowest energy, 7.7 GeV, although with the large error bars, the signal, the measurement and the background are consistent with each other. But in between, like 200 GeV, 27 GeV, and others, we seem to have the observable above the background, unless we are looking at very central collisions. And this is reasonable, because in very central collision, you do not expect a strong magnetic field. You have almost no spectators. So how do we understand the 2 extreme case? At the very low beam energy, it's easier to understand, because we expect there's no QGP, no chiral symmetry restoration, then no CME. So you are not supposed to see CME there. But at high energy, LHC energy, we should have QGP, right? So the reason is the duration time of the magnetic field. This lower left figure shows the calculation of the magnetic field as a function of time in the vacuum. So in the vacuum, the magnetic field will drop like a stone. It drops exponentially, especially for high collision energy. So the red represents the 2.7 TeV, and this is the impact parameter of 7 Fermi. Initially, at the higher energy, you do have higher peak magnitude of the magnetic field. However, they drop very, very quickly, much faster than the lower energy. So by the time of 0.1 Fermi over C, so before you even create any quark or gluon, this magnetic field is already lower than 200 GeV, shown in blue, by 2 orders of magnitude. So that means through this simple illustration, at LHC energy, we should not expect the magnetic field to really kick in to start the chiral magnetic effect. And for lower energy, actually, we may even have a stronger magnetic field by the time we start to create the medium. So this can explain why we do not see this, and also in previous talk, why they should not see this. Then how can we control the background? So at least a few years ago, we think the ideal case is the Isobar. And by Isobar, we mean zirconium-96 and ruthenium-98. 96. They have the same number of nucleons. So strong interactions are almost the same. However, they have the different number of protons, different by 10%. That can be converted into the magnetic field squared difference about 15%. Then the flow-related background, we can utilize the delta gamma divided by V2 to mitigate that part. And non-flow related background are almost the same because the two systems are so similar to each other. So then we have some realistic estimation based on the statistics and on the error bar. So our the estimation is based on 2 billion events per species. So what we get is if the background level is around 86% in our observable, meaning if the signal fraction is about 14%, then we can have an observable 5 sigma effect in the difference between the two isobars. So at least some detailed calculation how we arrive at this 5 sigma. So, and actually in the end, I will show that our statistical uncertainty, indeed, we reach this precision. But however, we didn't see the 5 sigma difference. So that's the bad thing. And also, one concept is FCME. So FCME is a fraction of the true CME signal in this observable. So I will mention this again later. So the experiment of the Isobar collision happened in the year 2018 at RIC. And STAR successfully took the data. And after 3 years of many people's effort, we published the first paper on the Isobar data. So during this analysis, within these 3 years, STAR carried out a blind analysis. So the blind analysis contains several steps. So initially, we use so-called mock data challenge. So we use gold data to pretend it's Isobar and use it to test the code. Then we use the Isobar mixed data. So we mixed, it's a mixture of the two Isobars, and no one knows what they are. And we further test the code. Then the code is frozen, so no one should be able to change it anymore. And everyone will be able to run it. So it took more than a year to do all this. Then the blind analysis, we start to do the QA of the data with 1% of each of the Isobars without knowing which is which. This QA procedure took half a year. Then in the end, after we run all the analysis, we unblind the data. So it took a long time, but we think it's worthwhile because this guarantees there's no, or there's minimum artificial mistake from human mistake. So STAR formed a blinding committee to decide how we should do the blind analysis. So they published a paper on this method. And there are 5 groups of independent study. So each group ran the other group's code to avoid any further artificial effect. So this is the sequence. For example, UCLA will run Stony Brook's code, and Stony Brook run BNL's code, and so on. So no one will know the species-specific information until unblinding. And also, everything is documented. If something is not written in your document, you are not supposed to do it. And we have to follow everything strictly. So even the interpretation have to be predefined. So it's very strictly followed. So before we do the physics analysis, we need to define centrality. And also, we have a separate group of people who is dedicated to do centrality definition for us. So we do not do that. And the centrality definition is doing with the global fitting to the real data. Okay, I will be faster then. Global fitting to the real data. So global use Wu-Saxon parameters. There are 3 candidates. 2 of them use the same radius and the neutron skin, but different deformation of the nucleus. But the third one consider all the isobar to be spherical, but they have the different radius and the neutron skin. So then we fit and see which case give a better fit. So that will be the final definition. So in the end, we found case 3 with a thicker neutron skin in zirconium. That gives the best fit. However, we found some trouble. The trouble is with this definition, when we look at the multiplicity as a function of centrality, the 2 isobars are not the same. There is a few % difference between the 2 isobars if we use this case 3 for centrality definition. Actually, if we use case 1 or case 2, this ratio is very close to 1. However, we are doing blind analysis. We have to follow the procedure. So then we have to stick to case 3. And this is the root cause of some trouble I will show. So then I will show V2 and the delta delta. So these are both related to the background. So initially, we hope the background should be the same for the 2 isobars. However, they are not exactly the same. For V2, okay, I should mention that we have 5 different sets of results. And I'm only choosing the one with the smallest error bar as a demonstration. So V2 are different by a few %, 1%. But this is fine, because we can do a delta gamma divided by V2. And delta delta is also different by about 1 or 2%. This is also fine if we divide it out. But when it's below unity, actually it can fake a CME signal, because the CME signal can cause this ratio, delta delta ratio, to be below unity. But later I will show that actually this is not true. We have some way to have a better comparison. And in that, this ratio is above 1, not below 1. Then we look at the CME sensitive signal, delta gamma and kappa. So delta gamma is below unity. And what's more important is delta kappa, when we normalize V2 and delta delta, it's also below unity by 2%. And this is hard to understand at the first glance, because if you don't have CME, you should be at least 1. If you have CME, you should be above 1. How can you explain you are below unity? And this is just because the centrality mismatch or the multiplicity mismatch between the 2 isobar. So what we can try, this is after the blinding analysis. This is based on a few author paper. So when we take the star data, delta delta, delta gamma, and the kappa, and we switch from the centrality definition to the matching multiplicity. When we do that, you can see for delta delta, initially it's below 1. Now, when we switch, when you match multiplicity, it's above 1. And for delta gamma, again, it's a qualitative change from below 1 to above 1. And what's more important is the kappa. So previously, it's below 1 by 2%. But now, when you compare them at matching multiplicity, really they are consistent with unity, which means we do not see a signal. But this is a more reasonable scenario than below unity. Then we can have some estimation, because this kappa ratio is related to FCME, the fraction of the CME. There's a factor 15%. That's a magnetic field square difference. Okay, so if we switch the x-axis from centrality to multiplicity, we can see everywhere now it's consistent with unity. And we can convert the error bar then into an upper limit. So with 95% confidence level, we found that FCME is around, the upper limit is around 4%. It's a very low signal fraction. And so post-blinding, STAR has also re-estimated the baseline. And now you see for the, yeah, almost done. Oh, so you see for the data points, the bands, the colored bands, represent a new baseline. And that means we do not, so the measurements are consistent with the background. We do not observe the CME signal in the Isobar. And the reason why FCME is so small, so we can show that in AVFD simulation. If you use the true reaction plane, actually FCME is similar in gold and Isobar. Unfortunately, we use participant plane. When we use participant plane, the Isobar have a smaller FCME, about half compared with gold. And that's just because Isobar is a smaller system. You have larger fluctuation that increase background, decrease the signal. So it's like a double kill on the fraction. So the last two slides, I will show some bright side. So we do have some method improvement. For example, we can compare measurement using spectator plane and the participant plane. And they have different sensitivity to the signal and to the background. So in the end, we can have a FCME related to this two measurement and with the ratio. This ratio can be measured with respect to the two reaction plane. So when we look at gold data, we do see seemingly some finite FCME signal, although not significant enough for some centrality, like 20 to 50%. And almost the last slide is the event shape selection or event shape engineering. We can try to use the flow vector to control the event shape. Then simulation show that if you have AMPT model, this method can get rid of the background. V2 can go 0 when Q2 is 0. So the pure background can vanish. Then the right figure show some example of the STAR data. When they use this method on 27 GeV gold, they do have a finite intercept. So that's a promising signal. And okay, as a function of centrality or multiplicity, there seem to be some finite signal, although we still need some further investigation on the origin of this. Yeah, so summary, I have mentioned everything. Although the past measurement indicate some charge separation, it could be contamination from background. And Isobar data, we do not see any predefined signature. However, we should focus back on larger system. We should try different event plane types and different event shape selection. Also, the lower energy may have a longer duration time for the magnetic field. So we are still hopeful. So thank you.
Thank you. We have time for one question.
Very simple technical question. Why there were no proposals of Isobar experiments with much heavier ions? Is that impossible?
So when it's much heavier, the relative difference in the charge is smaller. It's hard to find something still with 10% difference and larger. Yeah.
Right. Makes sense.
Okay, maybe another quick question. Okay. Thanks again, speaker.
Thank you.